All right. Good. So now let's start with some modeling, right? How the data are generated. See, all the generative AI is trying to learn from data samples what the distributions are, right? But here, let's do the analytic approaches, and we start with the model. We think how the data is generated. For example, here, right? So we think that the Y, those columns of Y, are generated by, so those samples Y, right? Those Y are generated by some matrix, and X has follow certain distribution, right? To be simple, we assume Y is generated by some linear transforms, right? The Fourier or wavelets is one such form. It's a square matrix. We will worry about long square matrix later. If this is a square matrix, usually this is called a complete basis. Okay, 完倍的G 啊。If D is there are more columns than rows，一般情况下 D 是 fat matrix，那我们叫做 overcomplete。如果是 D 是一个 skinny matrix、tall matrix，it's called underdetermined， incomplete matrix。Okay， so this is the terminology. Let's start with the complete one. This is the most important one because Fourier transform. So you can think about it. If Y, if it's a lot of sum, right? If you learn properly, if you have a lot of sum collection of sum, if you learn the optimal transform, D should be recovered Fourier transform. 明白吗？对吧？你根据我的数据来决定它最佳的 transformations. Or could be a wavelets, right? So we pretend we don't know D. We only have Y, many columns. And we assume Y is generated by some dictionary, square matrix with the superposition of the columns. X 非常 sparse， 就是每一列X， 对不对？每一列 X has only very few non-zero entries。所以就是很简单，就是相当于 Y 每一列的 Y 就是通过这个 X 每一列的 X 选择 D 里面的很少的几个列，做它的线性叠加生成。Okay, it's a very simple generation model. So that's how Y is generated, right? D is my dictionary. 每一列就可以看到每个列就是一个 words. Then use a linear combination X, choose a few words, combine to sentence Y. 明白吗？ So Fourier transform, wavelets are just special case of this. And how do I model sparsity of X? X should be very sparse, right? Then it's actually you can model X with the two most important distribution in the world, right? 你们学过统计，那么你看统计里面学个概率里面最重要的两个分布，这个模型都有，一个叫高斯分布，一个叫 Bernoulli 分布，对不对 ？Bernoulli 分布是个离散的分布，什么意思？就是说这个每一个 X has its column, right? So it's a column vector. Whether about certain column is zero or non-zero, the Bernoulli decide with property theta. Theta 是0到1，对吧 ？theta 非常小，比如1/1000， 0.01 theta, right? If theta, you choose the theta, the draw Bernoulli distribution. Decide it's a binary, right? 1/1000为1，1/1000不为0，啊，就是9.99都不为0的，对不对？所以 once it's 不为0。You decide each entry is 0 or not 0, right? That's what the Bernoulli, the theta decides, right? So basically, theta will decide how sparse the column X is. Once the entry is non-zero, then I have to choose a weights. The weights you draw from Gaussian, 知道吗？所以就是 Bernoulli Gaussian model 啊。首先用 Bernoulli 确定这个位置是0还是不为0。如果不为0，在高斯里面取一个 independent value。Arbitrary value, Gaussian distribution. So X just a composition, entry-wise multiplication of omega and G. Omega is Bernoulli distribution. G is the entry-wise multiplication of the two matrices. Here's thinking about omega is a Bernoulli matrix. Each entry is 1 or 0. When 1 shows up with property theta, 所以 theta 就可以控制有多少个非零项，对不对？多少个1啊 ？theta 越小越 sparse。G is actually controlled Gaussian， 对吧？好， Turns out this can be simplified, right? Then D can be arbitrary embedded matrix as long as it's invertible. D can be any embedded. That doesn't have to be of any structure. Turns out with a little bit of preconditioning, if I see such data, I transform using the data process itself to some preconditioning, that I can assume the D becomes orthogonal. 虽然这个数据啊 in general, the D matrix, the square matrix doesn't have to be, it can only be a square, it doesn't have to be orthogonal. But if you do process your data like this, this actually will be equivalent as the D become orthogonal matrix. 啊，正交矩阵，对，它是变得这个字典可以变成是正交的每一行，每一列啊，所以 make it the job is a little bit easier. So hence, by assuming your data is generated from the orthogonal complete matrix, you don't lose generalizability. OK， 假设你的数据这个D不是正交的，你可以先预处理下来的数据啊，变成正交阵乘上一个系数矩阵啊。That's actually the understand. So this is so sometimes a little bit of math is useful, right? And reduce something looks more general to something more special. So yet you don't lose generality. Right. So that's actually the thing, right? So now we actually consume, but data actually has this form, right? It relies on many orthogonal k-dimensional subspaces. It's a mixture of low-dimensional orthogonal subspaces like this. Okay, the question is, how do you identify the subspaces? They're not aligned with the coordinates, right? They're actually in the general position, right? Actually, how do you find the vertical directions? That's the question. So there are many ways to do this, right? So for example, right now what do we know? We have y, we don't know the d, but we know d is orthogonal. We don't know x, but we know x is sparse. That's it, right? Those are two pieces of information we know. We have to use this two pieces of information to solve this problem, right? Solve the set of equations, right? Set of bilinear equations. It's actually homogeneous, right? Y could be millions by millions. There's many variables. So follow the lead. Right? So the questions are set to notice that, say the x is sparse. So then if you look at the y could be very fat, right? Y looks like the, so this a little bit. Right. Both x and y could be like this, right? Very fat, equal to something squared. That's d, this is the y, equal to, sorry, multiply x is also very fat, right? Basically, you have many columns, right? That's number of samples, right? The dictionary is square n by n, right? This is n by p, right? This is also n by p, right? X. But x is sparse, columns wise, row wise. So each row is also very sparse. Now, if you look at this, right? The row of y are just a linear combination, right? Each row here hit this matrix to a weighted sum of those rows of x, right? Each row here is a linear combination of the rows of x. And also rows of x is sparse. Therefore, the row of x span a subspace in Rp, right? P 很大. This is a subspace. This row spans a subspace in Rp. And those sparse vector actually is in the same span of those. 就是在这个子空间里，在子空间有一些 right? This span is exactly the same. 因为这个就是这些 row vector 的 linear combination 嘛。So they should span the same subspace. So hence those sparse vector are hidden inside the subspace spanned by the row of y. That's what this says, right? So therefore x0 forms a sparse basis for this span. But it's somewhere in that subspace. We don't know where it is, right? We know why. We know that subspace, right? Spanned by this guy. But we know it's hidden somewhere. There's some sparse vector. How do I find those? Right? So this is a question. Can I find? I know this row is in this here. So there must be some linear combination of these rows of y will reproduce this guy, right? You show if you hit, where's my? If I compute the D inverse, there exists beaver D inverse, right? If I hit this guy, so I should be able to reproduce y at this x, right? This is y. This is the inverse. So if you look at it in the D inverse, the first row, multiply the column, the rows, right? Is doing a superposition of the rows of y that should regenerate in this row, right? So therefore, there must exist a vector q, multiply the rows of y, give me the first x1, which is sparse. 对不对？这个想法很简单。Right? So we have to find that the linear combination of the rows of y so that you'll be able to reproduce one row of x, which is sparse. Can I find such a q that is to recover one x? Of course, there are n rows here, right? D inverse has n rows. 每一 row 会 recover 一个 row of x. So I have to find, repeat doing this 10 times, n times. I should be able to find all the rows of x. Right? As long as finding. So this, if you actually figure this out, so now the question becomes, can I find a q, which corresponding to the first row of the inverse, D inverse? I don't know what D is, but I don't know q either, but it doesn't matter. I'll find the q such that there's such a q exists, right? Find a q such that hit the rows of y, give me the sparsest possible, which has zero norm means count how many non-zeros, minimize how many non-zeros there is. Right? Of course, that's a very hard to minimize. Turns out this is a P hard to minimize, right? One way to do it, that's actually the first 10 years of the century. People figure out how to solve this kind of problem, right? Instead of doing zero norm, they're doing one norm. 所以这个世纪的前10年，大家在做压缩感知就在做这件事情一范数。Even Americans claim the 21世纪是一范数的世界，对不对？一范数的世界当然现在认为是 AI 的世界深度网络的世界接入 AI 的世界。Anyway, doesn't matter. Whatever they claim, right? Let's just at least say how significant that is. Okay. Also, we know the history, right? Actually, first 一范数是最早提出来的。比二范数还早，对不对 ？Boscovich 最早拟合线性代数的时候，线性拟合的时候 ，proposed to do 一范数用法。OK, some absolute value. So next lecture at one point we'll talk about this, how to do L1 minimization. Right. So in order we want this to be sparse, the result of this vector to be very sparse. The zero norm is very small. So it turns out that you don't have to do this. You only have to do one norm. Now this is much easier. Right. This turns out to be combinatorial, a PR. But this one, originally people thought this is a PR. Turns out it's not. Right? This actually can be solved very efficiently under very banal conditions. Right? So that actually needs to the. But this is very hard. But even one minimization has some caveats. Right? 一范数是这个样子 right? 它一范数 one norm is continuous but not smooth. 所以求导数的时候会有点麻烦，好吧？ We cannot take derivative of the one norm that easily. So next lecture, at one point we'll talk about how to deal with that. Right? In the first 10 years before the neural network, people are sort that including me, we're trying to figure out how to do that efficiently, very quickly, very efficiently, and then with theoretic guarantees. Right? There's a whole host of this. Actually, that's my previous book is precisely all about L1 implementation. Right? No, but it turns out you don't have to do this. At least for this problem, you don't. I actually can do something you maximize the L1, L4 norm. So it turns out this problem is to a large extent equivalent to this one. 这两个问题呢，等价，几乎是等价。But the 4 norm is easy, right? 4范数都是光滑，4次方啊，求导的光滑，1范数很麻烦，绝对值对吧？一取绝对值再求导就麻烦了，对不对？好，this is actually formal to maximize it equal to this, right? Why? It turns out there's actually beautiful geometry behind it, right? Minimize a one norm, right? So if you growth a one ball, 一范数的球像这样啊。If you grow for small, first you touch those sparse vertex, touch those axis point, the sparse vectors. See, those are sparse vectors, right? 这个 vector 不 sparse， 两个坐标，对不对？这个是一个坐标对比，这个是一个坐标对比。所以你看 ，if you grow a one ball, the vertex touch this sparse vector first. So you actually need to minimize a one norm. You find those points first. Now, circle 各项图形，对吧？根本不管它是 proposed partially or every vector， 你看各方向这些都是一样啊。所以2范数是不管你这个解是稀疏的还是稀疏啊，分子都一样。4范数不一样啊。4范数 looks like this. Now, if you maximize it, if you shrink alpha ball, those points touch the vertex first. It turns out geometry, they are dual to each other. Minimize one norm. So maximize form 在几何上是有点对偶的感觉，好吧？对，它是 actually split out. They're all promoting spikiness of the solution. So this is intuition. Of course, if you want to know the rigorous justification, go read that entire book. Right? Yeah, that 600-page books, you can actually get a full blast of it. But for now, just take my word for it. Okay, you have to know. So this is actually turns out we don't care about the explaining why. We care about how. Okay, here that. Now, but this is also a little bit awkward, right? Remember this. Even I can solve this problem. Even I can solve this problem. Even I can solve this problem. You only find one row, right? 那我还得重新再做一遍，对吧 ？Find another cube. Minimize also is different from the first time. You repeat this n times. Fine, but it's still it's tractable now. You do this, at least it's doable. Although it's a little bit awkward. 啊，有点慢，有点笨，但是呢，至少你可以做了。原来认为是没法做的 ，OK， 难做了。至少这 So turns out how well this works. Also turns out you don't have to do one row at a time. You can do all together. Right? Find the n by n matrix, orthogonal matrix, such that the maximum norm is optimized. 对不对？我把这 n row 同时找它，找 a matrix， 我把它 d inverse 看着不好看，我就把它叫做 a， 对不对？取个名字叫 a 啊。Find a square matrix A, which is inverse, corresponding to the inverse of D, right? So such that the whole matrix, AX, AY or matrix becomes sparse. And also I try to enforce A is orthogonal. A transpose A is identity, yeah? It's enforcing. So it becomes, so this becomes a maximization subject to this constraint. Right， 这个是 measurements， A 不知道 ，X 不知道，但 A 是增加的 ，such that X is sparsest， 最稀疏的。Right. So there's a justification. If you care, but there's a justification for this. But at least we care about the optimization, 对不对 ？Very well. Turns out that we're not the first, right? The L4 norms. So I started working on this problem at Berkeley, data dictionary. So then we did a little bit of, we were trying to prove something about the optimality. We'll talk about that later. Is that I start asking around, right? Because this one has beautiful geometry. We'll see that later. Geometry behind is beautiful. It's our form of maximization and so on. Right? So we start to dig around. Anyone has done this before, right? Before everybody's doing one minimization, now we find that L4 is actually much more beautiful, right? So some global geometry is beautiful, landscape is beautiful, it works much better than we expected, than anything else, right? We started to dig around, anyone has done this before? Turns out yes, right? Very interestingly, we found that actually one of my former academic advisor, math advisor, as I was asking my former Alan Weinstein. Alan Weinstein is my master advisor when I was at Berkeley. I did a master in mathematics with him. He's a student of Chen Yingzhen, right? So I actually asked him, right, this has a beautiful geometry. I said, anyone know this? He said, oh, Yi, we did this in the 1980s, right? 这个他有一篇文章，他说他是80年代他就在做这个示范数优化。我说 how？他说 because we're trying to solve 量子力学里的 quantum mechanics. Turns out, yeah, that's true. Turns out, 量子物理对不对？最可能的，对吧？最可能的路径是概率最高的路径，对不对？啊，经典的路径就是概率在量子模型里面的 highest probability, right? In order to find that process, turns out it's alpha maximization. So he wrote a paper with Lu and so on, his students, Alan Weinstein, W stands for Alan Weinstein, right? They actually did this. In fact, he claimed that because we're curious about the global optimality, I'll talk about this later, right? I say anyone has proven it's optimal. First, I called him up. He said, "Oh yeah, we proved it." And later on, I found that he only proved the local optimality. Well, that's a different story. So, and you know what is Lu? 陆江华是我们港大的数学系教授。这是他的第一篇文章，他是李泽湘的夫人，是我们港大的教授啊。他是当时我的师姐啊。他的第一篇文章就是关于示范水文化啊，是很有趣的一个特征。Of course, this actually gets rediscovered, right? You will find 我不说过嘛，对吧？重要的东西总会被发明多遍啊，重要的事情讲3遍，对不对？总会被发明多遍。Turns out the ICA, right? 1990s, I told you guys, right? Hamanari and Oja, those guys work about. I told you these 2 guys deserve to win an award for deep networks, for sure. Okay. Hamanari is also the score function. Rediscovered the Twiggy's formula. Okay, score function. 对吧？所以我们今天有 stability 有 diffusion model, diffusion model 也是因为它。Okay. They actually designed the ICA. We'll talk about this ICA. They actually designed the algorithm for solving ICA, right? In fact, you can think about the model we introduced earlier. It's ICA model. Actually, this is a very much ICA model. Okay, just more fancier one. 漂亮一点啊。Of course, people do try to solve NP-hard problem, right? A bunch of people try to solve NP-hard problem. 现在认为最 promising 的 attack, long attack, using sum of squares. 这玩意儿也在用示范数，很奇怪啊。Sum of squares first defined operation 但是后来在做convolution neural networks 又在用示范数啊，挺有趣的。Right? How do we do this? Right? Why for makes sense, right? Let's just let's skip the detail. If you want the details of proof, you can read the other book. Take my course in high dimensional data analysis. But here we just take some for granted. So I have a bunch of data. Why? Remember, I have a lot of samples, right? Y has a lot of samples. This can be huge. It's a lot of data. So if I maximize, if I handle it with the square matrix A, unitary matrix, maximize for norm, turns out if I have many samples, essentially I take the average, right? This is essentially I'm computing the expectation, right, against the distribution. Right? Turns out this term is actually proportional to as if I maximize this thing. I'm actually maximizing the matrix A heading with dictionary. This is going to, I don't know it, but basically maximize this is equivalent. I'm finding A maximize this. Okay? Oh, this is interesting. Why? When this guy gets maximized, 示范数越稀疏的越大，对不对？ D is unitary. If A is what? 一个方阵什么时候最稀疏？每一行每一列有，不能是0啊，不能都是0。每一行每一列，对吧 ？normalize， 对不对？长度的1，对不对？那一行那一列变成最稀疏的时候是什么？ 一行只有一个一，对不对？一行也只有一个一。Well, when the matrix A, what's example? When A equal to one, D 是我们知道它是增交的，对不对？所以 A 是它的力的时候增交，对不对？当 A 是 D 的 inverse 的时候，A 是 D 的 transpose，正好它就变成增交正，变成 of identity, right? Becomes identity, so becomes a sparseness, right? So therefore, if you try to maximize A against the data you observe, this is equivalent to find A hit with the ground truth dictionary. That's what this theory says, right? So you expect this gets maximized when A is exactly inverse of the unknown dictionary. So you're looking for maximizing, finding A is finding the dictionary. You're learning the dictionary. Right. So how do we find this? Turns out the global maximizer of this exactly the identity or permutation matrix 的每行每列只有一个一的，不光只是 identity， 对不对？还有什么？我把行列交叉一下，对不对？所有的 permutation matrix is also 只有一个一，对吧？一全部都是零，对不对？所以 they're equivalent, but doesn't matter. Turns out they're all equivalent solution. So global maximum of D are the correct solutions up to sign permutation. That's it. Right. So basically, if you hit your data, minimize hit the matrix against your data Y, maximize our for norm, you are looking for precisely the maximum, the global maximum for that object function is exactly what you're looking for. Is the correct dictionary. And also you can actually show, right, how many samples. So remember before, right? Everybody believed how many n choose k, 对不对？我们至少要那么多嘛，每个子空间都会看一遍嘛。No, you don't. This is the magic of it. Turns out you only need n squared samples, so that if this is the maximum, you can show you only need up to this number of samples. This matrix, 你前面的这个 matrix 非常非常大 ，OK, very fat, OK, and it has to be exponentially many. OK, that's why even you can solve the optimization problem, the sample is so down. The number, how long the matrix has to be in order to allow this the A converge on the correct data. Turns out you don't. Turns out the only number of samples you need is only n squared, right? Then the maximum, the global maximum of this one is actually close to the original data, subject to a permutation. You actually can prove this, right? With nearly minimal samples, with high probability global minima of this close to the correct solution. 为什么这是 minimal samples? N squared samples. How many unknowns you have? N squared, 对不对？那是 n 乘 n 矩阵嘛，就是 n squared 矩阵，所以 n 个未知量，你总得有 n 平方个方程吧，对不对？所以 n 平方 is almost the smallest. Of course, there's a log term. It's nothing. 所以 n squared 是 minimum you can hope for to solve n by n matrix, 对不对？So how do we solve it? Now we understand, right? This is the right thing to do. This one does, if the global maximum for this one, give you the correct answer. And also it doesn't require that many samples. Why? Why does it have to be big, huge? Okay? So both global maximum of this is the correct answer. And also you don't need that many samples to, if you can find the global maximum of this guy, you don't need that many Y. Once you can find it, you're done. Right? You find the correct dictionary. How do we find it? 所以我记住啊，我一直马老师一直在讲啊，任何一个问题 ，right? Computation, right? Now the mathematics tells you what the right thing to do, what you should do. Okay, you should look for the global minimum, maximum of this guy. But the question is how. 罗马知道了怎么去。What is the route? How do we compute this? Well, this looks a little bit weird, right? At least this with some constraint. We'll worry about that later. But this one is smooth, right? I can take what a is unknown, right? So we can take a gradient, right? 示范数很简单嘛，对吧？是次方导数求导，对，我们至少 we can do gradient descent, right? We can compute the gradient against against the partial f partial a, right? That we can compute, 对不对？期末下堂课那个王鹏老师会专门讲啊，这个知道吧？对不对 ？We take the gradient of that object function and then do the steps， 对不对？这个可以做吧？就是对吧？我 pop 啊，这是一个 climb hill 啊，computing the gradient 啊，最后肯定能走到山顶，对不对？是不是 global minimum maximum？I don't know，right？是不是真的是珠穆朗玛峰山顶，还是在某个半山腰的一个小坡上？I don't know，right？But at least I'm getting higher，right？So that's what we can do 啊。So actually do the gradient. There should be ascent because we are maximized. It should be ascent, not descent. But this is a little bit again, from an optimization point of view, this is also a nightmare. Why? This is actually a concave object function. So it's harder to optimize. And also with some constraints, right? This guy is a little weird. And also very high dimensional. It's huge. N by n squared. N can be millions. Okay, it's a huge dimension. So you don't know, right? So we try it anyway, right? Because there's nothing else we can do. So this seems to be the best we can do, right? Let's compute the gradient. Do the gradient. Of course, how do you enforce? See, the point that I start with A1, AAT. I take the gradient step. To that, but I add it to a step to this matrix. But then remember, the matrix needs to be orthogonal, right? So 正交正，但你加了这一步就未必是正交正了，对不对？ No longer violate, no longer orthogonal. What do you do? You project back, right? Normalize it, right? You make the matrix normalize orthogonal again. How do you normalize the matrix? 知道吗 How do you normalize the matrix? 把一个矩阵变成任何一个矩阵变成正交阵 ，question it. Now you have something much better. Right? Yes, question this is one way. Right? 也是高斯教我们的，对不对？是的，解高斯方程的时候 ，question this. Now you know something equivalent. It's much faster. SVD. Do the SVD drop the diagonal? Right? Here come. So now you actually have an algorithm. 上得四嘛，对不对？求导，在每个地方求个导，走一步，对不对？再投影回来，再走一步，再求导，走一步，投影，是吧？ This is called the project gradient descent, right? Project gradient descent. Enforce the remaining means reinforce the on this manifold of orthogonal matrix. 就所有的 orthogonal matrix 实际上是一个 remaining manifold, OK? 是一个 surface. So it turns out that we were playing with this, right? One of my students is playing with this. 一个 PhD 学生他在玩这个算法，大家反正这机器的方法没事儿，闲着不聊，大家就玩了，对不对？看看这个 how to convert. Then for gradient descent, what the first you do? Learning rate, 对吧 This is a learning rate. How's the step size? Which one? You can tune this guy to make it faster or slower, right? Choose different alpha. Remember what you guys doing? Learning rate, and you make it fast. So what the student noticed that he's trying to make alpha small, larger, small, larger. Then he noticed something very weird. First, he saw there's a problem. He found that he make alpha bigger the faster, the converges faster. Eventually, he made alpha almost infinite. Turns out converge faster. So what does it mean? So when this guy is almost infinite, which means that it doesn't really matter where you're a star, right? You always just do this. So why don't we just drop this? We only take this one, then project on SVD. So you drop this one, just take this is gradient, right? Just take this gradient, project on ON. Remember, the graph matrix becomes SVD, right? Just do SVD directly on it. So that's exactly what we do. You take the gradient, you take an SVD of it, and make it orthogonal. This is algorithm, right? And this is very interesting, right? If you look at the, so you do, see, you have the data Y, right? You match with the previous, the current A, you do a hit with the current matrix, AT. This is the problem from previous step. Then you do a qubit. This entry wise qubit stretch sense. Qubit looks like this, 对不对 ？qubit 把计算码的每个 entry 都能 skip stretch 一下。Then you hit it again. So we call it matching and stretching. Then project onto orthogonal. So turns out this algorithm converges fastest than anything. You don't do gradient. So is this still gradient descent? It's no longer a gradient descent, right? So essentially doing this, take the gradient and project, right? So now if you look at the form of the gradient, look at the form of this matrix, this operator, right? So when this stop updating, 这个矩阵什么时候 converge？ 这个迭代 this iteration when it stops updating, when AT and AT plus 1 are the same， 对不对？当 AT plus 1就等于这个的时候，它就不再 update 了，对不对？所以 when you find this matrix, this equation will converge when AT plus 1 equal， 这是什么？这是一个 fixed point algorithm， 找一个 fixed point， 收敛到一个 fixed point。We'll get back to this in a second. All right, this turns out to be a very universal algorithm 啊，所以大家都认为 gradient descent 大家玩 deep networks gradient descent 实际上是非常慢的 very slow algorithm。OK， 你没有好办法之前。像自然界对吧 ？gradient descent 动辄就 take 1/3 iteration。从优化角度 ，gradient descent 是非常 ineffective， 所以 backpropagation 从优化角度是非常糟糕的。我们的大脑只有十几层 ，right？Any algorithm only take a few iterations, dozens of iterations. They're always we'll talk about that. 记不记得？收敛速度必须是指数收敛，对吧 ？gradient descent 就是线性收敛术，对吧 ？Linear convergence rate. So you have to converge exponentially. 前面我们已经看过一个算法，对吧？叫什么 ？You have seen a fixed point algorithm already. 我们算这个什么时候停止收敛？停止 update。ZT 等于 Z 的时候，对不对 ？It's also a fixed point algorithm. Both sides are equal. Right? Converge to fixed point for ZT plus 1 equal to MZZ. Also, power iteration. Turns out, 这个算法 this is a power iteration. It's contractive map. It's actually very, very powerful. We'll talk about this in a second. Right. So actually, it's not a gradient descent. It's a very powerful family of. You start with a gradient descent. A happy accident will actually end up with a fixed point algorithm, right? And turns out we actually interpolated this as deep networks, right? So if you look at the structure of this iteration, you can actually decompose from the original data all the way. If you repeat the algorithm t times, right? And you consider how the A matrix, this actually A transpose AT plus 1 is actually the increment from TAT to AT plus 1. So this is called matrix data. The matrix data is kind of difference. Because if you take the difference, turns out we actually can compose from Y to X. Remember, when you apply the correct matrix A to Y, you eventually get X. 对不对？所以每次迭代 A 矩阵都会gets updated a little bit. You can compose this A matrix into a sequence of smaller increments, right? So turns out this iteration is precisely applying a delta A1, A2, A3. Every iteration add a little bit to tweak the data a little bit to make it sparser and sparser and sparser, converge to X. So this is a deep network. Right? Even the transformation is linear. Even the transformation you're looking for linear, but I'm finding I compose that global linear transformation with many more small steps. Right? 为什么？因为我要找的这个 linear transformation 是 orthogonal，它有非线性结构。So I converge this. I'm looking for global rotation, right? So I rotate the data slightly, step by step, until I align with the sparse X. All right. And also you can apply to batches. Anyway, that's a different story. Actually, you can sort it out. Right. Okay, now let's look at the iteration. How fast is this, right? So we start with any matrix. We take a stretching, right? We run the algorithm to the dictionary. First iteration, sir, see, up to the third iteration, 已经找到了这个正确解，非常快，出奇的快。Right? So, see, we started with something we think is impossible. Turns out there is a very, very surprisingly, tremendously fast algorithm. How fast? You can actually even it's faster than exponential. 比这个 power iteration 比这个 PCA 还快。Right? You can actually at least around the global optimal. You actually can prove the convergence rate is actually cubic convergence. Right? So this is faster than exponential convergence. This is actually very, very fast. Right? And so if you because look at it, this one actually do a linearity, right? You do a stretching with a cubic function. Remember, in neural network, people do the sub-thresholding, random, and so on, right? There's just different approximation to this kind of thing. So you actually can do this again. This actually turns out, right? So that why this is actually true, right? It turns out that this actually converged to this object function has many local maximum, right? Equivalent, but they're all equivalent. Turns out. Right? Any solution is equally good because it's just subject to a permutation. Right? So you actually can find it. So it will take very quickly to one of the correct solution, right? So you can see that this iteration, there's a 50 dimension, 100 dimension. There are a number of iteration takes about a dozen convergence. 就12次迭代，非常快。So always insemination in experiments always converge to global minimum. We don't know why. So 有时候我们觉得，你看它的方程式它的 object function is very weird, right? Could be either concave, look like this, but there's no other weird local minima. Globally 非常漂亮。所以这个就是我们当时就想证明它是 global 的 optimal solution 存不存在？这个方程确实有些 local critical points， 但是你不会 stack up。Right now， 我跟 John Wright 现在有一个大概$1000的悬赏，就是这件事情，你看这个问题能找到这个算法能找到全局最优。找到这个示范最优化的全局最优，这件事情可以找到全局最优。Can anyone prove it? We can only prove with local optimal, converge local optimality, and also characterize what happens around global optima. 所以谁要能证明这个事情的全局，这个目标函数有全局最能收敛到全局最优解，power iteration 的解就是全局最优解This fixed point actually corresponding to this fixed point actually corresponding. The only solution to this is actually only stable solution to this fixed point is the global optimal，你会得到$1000，说不定我们可能把它提到$10000啊。过了大概已经过了5、6年了吧，6、7年了。我可以告诉大家这个问题有多难啊！我也不知道有多难，也可能很简单，I don't know。啊，这个问题我最早给的是张悦，张悦是我刚到伯克利第2年的，张悦是原来北大的第一名啊，数学那个奥林匹克金牌，北大的第1名到伯克利。当女朋友，他到伯克利第1年啊，在我那儿暑假，在我那儿做那个实习啊，我就把这个问题交给他，所以他就没有做出来，后来就炒股票去了。他花了2年的，张悦这个小伙子很了不起啊！他现在最近我们 release 一个高斯的那个 evaluation，也是他是 lead author，他是阿里巴巴数学竞赛头2届的冠军啊。然后这个后来去啊，他在 Berkeley 两年就把数学系的博士拿下来了啊，也是破了 Berkeley 的记录啊，数学系的记录。小伙子很有趣。那这个问题到现在为止他没有做出来，就是后来就是希望这个对，他没有被 traumatized 啊，这个是啊。It's actually beautiful geometry. I mean, he's a geometer. He studied differential geometry, right? As I said, this is beautiful. It's about the manifold. It's a defined, it's very well defined object function, right? It's a forlorn defined on the orthogonal group. It's a beautiful object function and orthogonal group. And you try to study its maximum and what the landscape looks like. Of course, there's many permutations and many local minima or global minima, but the landscape, what it looks like. You want to make sure the global geometry works out, that there's no local, points you get stuck. Okay, this is the gradient algorithm, right? And you show the only solution to that fixed point algorithm, fixed point equation, is a global optimal. 所有的实验表明，不让我不出实验都是对的。Yeah, all the solution, right? You can run many cases, tens of thousands of cases, right? On real data, right? So you can run, this is hundreds of experiments, right? You can run this, you can see there's a beautiful phase transition, right? As long as the number of samples, the ratio, this is the n, right? The ratio Pn is the more this, meaning that the more samples this way, right? As long as you can see, below this curve, meaning that the P over N is larger than some value. This is sparsity, depending on how sparse the vector is, right? As long as it goes above this curve, everything works. So 100% you find a global minimum, maximum, optimal solution. 所以这就叫对吧？相变啊，在高维统计和几何里面，你会看到很多这种现象。现在这些 computer scientist 没见过什么世面的，经常会叫这个什么 emergence。Scaling law 没见过世面啊，你说这个基本上是在数学和统计物理里面啊，这已经高维整定，这不提不谈了，对吧？水为什么会在0度变成冰，100度变成蒸汽，不是95度到105度，不是先变成降了，对不对 ？Why？ 这个现象 ，OK？ it actually is very clear, right? So the high dimension either it works or it doesn't work. Okay? Either you find a global optimal, or it never works. Okay, it's very interesting. And also you can look at the curve, right? Look like a quadratic curve. So you can see, right? Always like this. The number of observation almost quadratic, just like it's what like a theory predicted. But the theory only predicted the local around the local optimal. Okay, it's only about the global optimal around that local, but it's not a whole landscape. This experiment shows that doesn't matter where you start, doesn't matter how many random simulation you run, you always see this curve. Right? As long as the sample above a certain threshold, it's always give you the optimal solution. It's globally optimal solution. 那这个数学上就差一口气啊，我们能看到啊，就跟黎曼猜想一样，对不对？已经验证到对吧？几十个 billion 了嘛。The roots of the Riemann hypothesis, Riemann functions, right? It's always has on the real part is always the negative one path, right? So you actually can numerically verify, always true, but we cannot prove it at that point. But you can use it, right? Who cares? If you're an engineer, we can already use it, right? Then the mathematicians worry about it. 数学家可以去 worry about it. So We only care about this aggregate one. 那为什么4范数不能6范数、8范数呢？Why no 4? Why not 6? Why not 8? Yes, it works too. But turns out, actually, they converge faster. They converge faster. If you use 6范数、8范数，对不对？去 maximize. Actually, the algorithm converge faster. However, the matrix gets wider. You want to see get the correct convergence. You want to see the phase transition. 你要的 P 也更大 ，OK, for the matrix to concentrate. So there's turns out 4范数是一个最好的 compromise balance， 对吧？收敛速度很快，同时要的数据不多。哎，不要忘了，优化算法收敛很快，那只是 computational cost, right? It also has a data cost. How many data you need in order for the converge to the right solution? So there's a concentration to worry about. Turns out that 4 is a magical number, right? Just L1 is also a magical number, right? Minimize L1 is magic, maximize L4 is magic. 你知道陶泽轩吧，对吧？陶泽轩跟 Americanus 吧，写了一个 software package。陶泽轩在这个20世纪2000几年就在玩压缩感知，对不对？就在做一范数优化啊。他们觉得这神奇的不得了啊！一范数minimize 一范数。他们有一个，他跟这2个世界上，一个是纯数学家，第1名的纯数学家，一个是应该是数1数2的数1的应用数学家 ，Americanus， 他是现在斯坦福的数学系的系主任，对不对？陶泽轩是加州理工嘛，不，这洛杉矶吧，University of California Los Angeles， 哎，陶泽轩，他们俩一起就在神经网络热之前都在做 one dimension， 哎。而他们2个啊，这可是数学家啊，2个数学家写了一个 software package， 叫 L1 Magic， 名字叫 L1 Magic。他们认为 minimize L1 is very very magical，OK？ 所以在座的各位，数学如果不好的话，编程吧，对吧？即使数学好，也得编程吧，对不对？如果2样都不好，那我就没救了啊，那就没办法了啊。对，人家数学家都会编程啊，你们会不会去实现？明白吗？光是理论搞清楚，你要去实现。How do you realize it, right? Practically also very fast. To be a little bit quick, right? It's very very fast compared to. See, remember, there's a lot of heuristic algorithm for this, right? KSVD, a lot of subgradient, to do also gradient descent. Very many people to do L1. This is trying to minimize L1. This is subgradient. 汪峰老师下面会专门讲啊，you'll have a lot of blast with L1 minimization 或者什么叫 subgradient 啊？夏堂哥他会大概 briefly， 也不用理解太多啊，大概知道他在干什么啊。那这个就很慢啊。这个 KSVD 呢也不怎么 work， 很多的 error， 同时要花很长时间啊 ，takes a long time. But turns out this one is very very magic. It's very fast. See, the error is always very very little, always converge global minimum, and also very very scalable, very very quick, fast. In thousands of dimensions, takes just this is a very small machine, just on my computer. So with the GPU, you can be very very fast. So as I said, the global convergence still open problem, but everything else is known, right? Convergence rate, local locality, and samples, concentration, everything else, except if it's global, if that fixed point converges to global minimum. 谁要做出来对吧？很记住啊，你会拿到$1000啊。So you can see what's the difference, right? You can apply to the set of digits. See the basis learned from. See, this is PCA. We apply the images. Think about every image just a stacked pixel as a vector. Okay, many images of digit 0到9，啊，很多手写题的这个杨峰不就是在玩这个嘛？很多图你讲，比如 the letter let。The let stands for letter, OK? Letter let， 它用 CNN 去实现识别数字 ，OK？ 用神经网络啊，所以叫 the let 啊 ，right? So this is actually so now you use this one to you can see and as using the sparse, you learn you can get digit， 他学到的 dictionary 对吧？就是早学到前面几个啊，非常有趣，对不对？他学到的 digit， 他学到的 column looks like just like the digits. PCA doesn't。Weird, I don't know what it looks like, but anyway, yeah, PC 学到的就不是跟这个0号到9啊对应的。 right? You can see now that this is using this is the top one basis, top two to approximate. If you have the top two to approximate all the digits, right? What they look like， 也就是用两个，基本上用三个、四个就已经很像了，对吧？这里还是很糊的，对不对？第一个基本上是乱的，第二三个前面就是很乱、很糊的，PCA 是比较糊的。It's not very sparse, right? So you have to take a lot of PCA bases to be able to approximate the data. Right? Here you can use just almost 10, almost perfect. So some generalization, right? So how is this connected to PCA? Right? Turns out it actually is connected to PCA and also ICA very closely. But right now we hit the data with the whole rotation, right? 想把这个整个的 basis 找到啊。We hit A the orthogonal matrix is the full rotation. What if I just like PCA? I don't care about the whole basis. I only care about just a few top ones. 对吧？比如说这里 I don't care about all the rotation, right? I only care about the first top, let's say top 3 or 4 or 5. Right? I only care about what is the top 5 basis to sparsify data. Right? I only care about the top 5 to make the Y sparsest. Right? Can I do that? I mean, this is still very expensive, right? This is n by n, right? N squared. If K is fixed, I only care about top 5 or top 10. And at least it's linear. And n can be hundreds, thousands, 10,000, right? N can even grow. But the K is I always fix with 50. I'm done. I only want to top 50, sparsify the data, right? The data. Can I do that? Yes, you can. All you have to do is just instead of hitting it with a n by matrix, hit it with the top matrix, n by k matrix. Okay? You choose fixed k. Hit it with a 扁矩的矩阵，但是那些矩阵它也得这些 column 也是增加的。Incomplete basis, right? This we call this incomplete basis. Right? Just hit it with top 5. Okay. 就有点像 PCA 一样，对吧 ？Top 5, top 10. Fixed K and hit it with a small matrix. Turns out you can write it down with a little mathematics. You actually write down the algorithm. It's exactly the same. The compute the gradient, project on the manifold. This is actually no longer called orthogonal. It's called a steeple manifold, right? K n by k orthogonal matrix. It's called a steeple manifold. 所有的 n by k orthogonal matrix columns orthogonal are called a steeple manifold. 所以就投影到上面，同时投影一样用 SVP 就好了，取前面的 k 个啊，非常简单，一样 ，nothing changed actually, except you just take the top k. Right? So you actually can do. See now you can unify everything, right? PCA. What PCA is doing? PCA is actually headed with the top n by k matrix maximize 2 more for Billy score. 那么现在 L4 norm sparsify, you want to sparsify, you maximize 4 norm 对吧？明白吗？就是取个不同的 norm 而已。好，所以看 PCA 是找到一个子空间，把最多的能量保留下来。这个是找一个子空间。head 我的数据把它变成最 sparse， 变成最 spiky， 比如说 entropy 最低，这个是在 maximize 能量，这个是在 maximize 能量，这个在 minimize entropy， 啊，非常有趣吧？对吧 ？That's it. They're actually quite the same, except just all the functions are different. Constraint 都一样啊。Then how they're related to, so basically, the PCA is find the type uncorrelated projection with large sample variance， 就是 PCA 在做，对不对？这个是 find the top K uncorrelated projection with large first order moment， 是更 sparse。从统计上是 find the largest fourth order moments， 对吧 ？This covariance, this is second moment， 对不对？这是 third, this is fourth moment。啊。What else is doing fourth moment? ICA 在做这个事儿 ，turns out， 说 have an error， have 那个 Oja， 他们在97年啊 这哥们儿在弄 score function 之前在玩这个 OK。对，actually they're using IC to justify. As I said, right? IC is the justification for，不 PCA 都是线性的嘛，你为什么要非线性的 threshold 呢 ？IC 需要这个，待会儿你看啊。So you want to identify the one equivalent. Well, of course they're doing one at a time, so it's a bit awkward, right? They only care about one of them. So actually, they propose to do this, right? But see, guys, if W is normalized，这像是常量，对不对？If W is a unit vector, this is just one, right? So only this one work. It's actually L4, so they're also doing L4. So IC is also. So they actually proposed the algorithm to the ICA. So PCA, you can see, is about power iteration, right? 看过，对不对？那么 ICA 呢 ，maximize for more。你把这一条，尤其是当然他们做的有点 awkward，当这件事情等于一的时候，这项事情就丢掉啊，这两条都存在，对不对？那么就这个。Right. Now, they are of course dictionary, especially generalized version. Exactly, you do multiple ICAs simultaneously, right? You hit with the K，你找你把头 K 个都同时找出来，他们就只找一个嘛，那我们就要找 K 个同时找，right? You find all K W, so you find this object function. 所以你们看 ，this is object function takes a gradient projection. This is object function takes gradient takes gradient takes a projection. This is object function value takes gradient takes a projection. Like that. And the algorithm iteration always converge, stop converging, stop updating when reach the fixed point. Stop updating when reach the fixed point. Stop updating when reach the fixed point. They're all power iteration, by the way, and extremely fast. Right. This one is even faster than this one. This is geometric. This is a cubic. 就是在优化上，这叫线性收敛数，实际上就是几何 error 按照次数往下跌啊。这个都是 cubic 收敛数，说比线性收敛还要快，至少 locally 啊。Now we'll try to understand neural networks a little bit. What's going on, right? So remember what Newton invented. Why Newton invented the Newton algorithm? Newton is trying to solve polynomials, right? Find the roots of polynomials, right? He knows that beyond 5 degree, if f is polynomial function, you want to find the roots of the polynomial, right? Because if the f is polynomial of degree higher than 5, they're still closed form. So you have to do it numerically. And he said, how do we do it? Well, solve the fixed point algorithm, right? So this has everything, right? So the modern geometry, but everybody thinks Newton algorithm is the second order algorithm. 实际上不是，Newton 实际上是 first order. 当然我们讲 his job is find where it cross zero, right? The function where it cross zero. How do you do that? So if you are here, it's a random guess, right? Of course, there's an error. This is why it's not zero. Yeah. But this therefore fx is the error, is exactly the residual. Okay, the error. So how do you reduce that residual to zero? You find how fast this one decrease, right? Find the slope. That's where how fast around that point, how fast you cross the zero. Using that one to approximate this. This one is exactly find what the x point is. Until left and right gx equal to x. So this is Newton descent, right? So how to find it works like a charm. The y becomes quadratic. Why everybody using Newton method using we remember right before the Newton method is the first second order method. 为什么？明白吗？明白。 Newton is trying to find the roots of fx, right? What if you want to find the minimum of fx? What do you look for? Look at the maximum or minimum, right? Minimum 的时候是什么 ？You're finding what? What's the condition when the function becomes minimal or maximal? The gradient of f becomes 0. Hence, x is the roots for the gradient of f. Apply that f, replace that f with this one. You get a Newton's equation for optimization. Okay? All right. This becomes gradient, this becomes Hessian. That f. Maybe I should call it G. There's so many f's, all right? This is G. Replace f with the gradient of G. You get a Newton's algorithm, right? To do optimization, to do gradient set, right? And this becomes a Hessian, this becomes a gradient, and this is a gradient set. Understand? As you try to find the zeros of the gradient, and this is the minimum and maximum. And so you can see this is now everything we do here, right? It's a fixed point. 这个东西什么呀？ This is residual network. So residual network is just reinvention of optimization. 就是学计算机的同学数理优化不好，觉得神经网络在干什么？神经网络是在算在实现优化算法 ，optimize something, find the roots of it. Okay, that's it. Nothing else. No mystery. Okay. 所以现在说什么神经网络是神秘的不得了 ？No, nothing. Okay, it's completely transparent. It's just another terminology for realizing optimization algorithm. Okay, find the residual, correct, tells you how to correct it. Now look at this. Hit your data with some linear transformation, normalize it, and project it. Do some nonlinear projection. And repeat doing it until you're done. Okay? Until something gets good enough. Okay? Until this becomes sparse enough, you can assign labels. Right? Classification is exactly doing this, right? 就变成0100000啊01100，right? That's what you're doing. Straight. So everybody is doing Newtons. 所以我说太阳没什么新鲜事儿 ，OK？ 不管你怎么取名字，不管你怎么绕，不管你怎么弄，对不对？就做这个事情啊。Learn the dictionary, right? Learn W, hit your matrix, hit your data, update. 只是呢 ，W 要去学的。要去 update 啊 ，whatever back propagation， 所以好，最后几分钟呢let's try to talk a little bit about this, right? But this one is still very idealistic, right? I assume my data is y equal to the data I observe. You remember, here I assume my data y right? Y is generated this way, 对不对 ？Y is AX， 哪有这么干净的数据啊？我这边 is so clean, right? Y equal to GX 0. What if there's noise? What if there's outlier? What if data is incomplete? 对不对 ？What do you do? So guys, we're still living in the 象牙塔, right? We're still in the ideal world, right? That's why you see those beautiful results, right? What if the world is a bit real, right? Right. This is what we see, right? So far we're looking at data precisely on those subspace, right? But what if they have noise? If Y has some noise, Gaussian noise, what do? Does this still work? Yes, it does, right? So you hit your data with such noise data. YA is noisy now. Turns out that again, you have just with a little bit more data, it still concentrate. This actually converges to something like this. All right, you actually can prove it. If you have noise, the large data still concentrates. It's very, very amazing. And you can also add noise, outlier. See, this is clean data. This is from the substrate. But you can also add columns has nothing to do with the model. 对不对？就跟这个 picture 一样啊。Add some red dots, right? First, see, those are the adding some noise, right? To perturb those points no longer on the substrates precisely, right? And then also I can add some complete outlier. Has nothing to do with the subspace. It's the red dots, right? We call it outlier. It's contaminate, right? Actually, 你不知道哪个 column is good, right? Okay, you don't know which one is right. Contamination. Turns out it's not that bad. Again, you can check as long as the fraction of outliers is for any random Gaussian, depending on that plate, below the data with outlier G, right? So as long, hold on, why this one I think it's running out of battery. If this one work? Does this work? Hello? Yeah. Does this one work? And this one also receive. Yeah. This one is running out of battery. Yeah. And so I suppose everybody can hear me. So now under very general conditions, if those are the outliers, again, this one actually is actually the expectation of this one is close to 0. Hello? This one doesn't work. Hello? This one also running out of battery. Hello? I think this one is running out of battery too. Yeah. Can you guys make sure it's charged? Hello? Can anyone on the Slate can still hear me? Hello? How about this one? Does this one work?
Yeah, we can hear you.
How do where is receiving the, I don't know which one is receiving me. All the time. But this one is running out of battery. How about this one? Can you hear me now?
This works.
Does work?
This one works.
All right.
You can see the green.
So now I'll just use the screen then here. So you can see that if you have an outlier, as long as they're independent, statistically it actually does not interfere with you hit this result with the one norm. Okay, you actually can hit even the data with the outlier as long as they're sort of independent to your data. It turns out it still also concentrates. It's very amazing, right? So this looks very weird problem, right? Almost challenging, but turns out the data speaks for itself. If you do this kind of maximization, it actually is a number problem. Also, you can crop the data. Remember the entry of Y. You can also crop with gross errors, right? Not just adding noise. You can pick a fraction of your data point, the matrix. Remember, B is a Bernoulli matrix, and S can be gross. S can be infinite, negative infinite. Don't care. Pick any distribution. As long as the B is non-zero, you can crop that entry. You can select crop any fraction of entry, right? P is the Bernoulli, so it's the beta tells you what's the fraction of data you cropped. The beta can be 0.3, which means you cropped roughly 30% of the entries arbitrarily. Okay, beta can be 0% to 100%. Once those entries get selected, you can set it as to be +1, -1, whatever, right? The maximum value. And you don't have to tell the algorithm which entry gets cropped. So if you tell the algorithm which entry gets cropped, that becomes a completion problem. It's easier. Okay. Here you take the big matrix, you crop some entries, you don't tell the algorithm, right? 如果你告诉什么 matrix completion， 对吧 ？MAE 啊，什么 X completion 啊，什么这 completion 实际上是个简单的问题，因为我知道哪个 entry 是 missing 的，哪个 entry is corrupted, right? So this is a much harder problem. Again, turns out you actually can prove for such a matrix under very banal assumptions. Again, hit the data with expectation. Again, actually is equivalent to maximize the full norm against the ground truth dictionary, right? Actually, the rest term, the property actually does not interfere with the estimation maximization. It's very interesting, right? It's a bit hard to prove, but turns out it's very magically the case. So as you can see, so the 数据, if your data contains enough structure, if you have a fraction of corruption, fraction of outlier, certain amount of noise, they actually statistically, they do not interfere with this kind of optimization. Use an optimization to find the the global optima of this object function always associate statistically will always associate with the correct solution. That's the message. Does this work? Yes. So then you can do simulation, right? So much. You don't have, because for this course we don't require proof. If you take my other high dimensional data process, high dimensional data analysis, you have to prove this. Okay, you have to learn how to prove those statements, right? Using measure concentration, using statistical or probability theory to prove those statements. For now, you only have to know the L4 maximization works. You only have to know the matching stretch projection algorithm works, right? Then you can implement it. You can apply to data with noise, with corruption, with outliers. You can see that it converts perfectly to the ground truth. Right? For all the cases, and choose fraction of beta. See even 40%, right? Corruption still works. So this is actually doing a noise, outlier, corruption. You can see, right? Here, beta is already, I can see this is actually quite amazing. If you think about it, right? You can see in general, the number of samples, this number of samples needed, right? It's almost grows against the, it's almost quadratically, right? This is the fraction of the segmental amount of noise. Of course, the higher the noise, you need more samples. And this is the fraction of outliers. Of course, the more higher fraction of outliers, you need more data, right? But amazingly, you can see even the fraction of outlier exceed the inliers， 这也是1.5倍了，一样 work。这是非常非常 magical，right？ 有数据，大部分数据实际上都是 complete random outlier。但是你的真正有结构的数据是在里面一小部分 ，still concentrate. Very weird. We don't know why. Oh, you guys confused. Well, here is something very interesting, right? So remember, we try to take a matrix, we try to crop. See, we try to crop. Here I'm telling you, right? The B selection of fraction of entries to crop. Beta is the fraction, right? In general, we say if we wanted to recover a matrix, we only compromise, we only crop a small fraction, let's say 10%, 30%. 40 is already pushing it, right? Turns out, at least in terms of simulation, 60%, 80%, actually 90%, as long as the number of samples is large. In fact, theoretically, you can prove you can approach to 100%, as long as the samples size gets large enough. 90% of entries of matrix, it's arbitrarily corrupted, and you don't know which entry is good or bad. Still, the L4 norm maximization works. Will find you the correct solution. 这个我们上次看到一些人脸识别的，对不对？就是已经手回到你妈妈都不认识你了，对不对？所以这才叫 magical。我们现在看见的 emergence is nothing, okay, compared to how magical this is. 所以大家看了一点 scaling law 啊，费德的几条曲线，这就很了不起。There's no even explanation for this. This says a matrix, right? Every sparsify matrix has no dimension structure. I take the matrix. I take 90% of the entries, completely corrupted. I don't tell you which one is good or bad. But just by doing this simple maximize L4 norm, hit completely continuously hit this matrix, the data with such a simple process. I don't even have to know about it. I can find a dictionary, find precisely using 10% or 1% of the data that's still intact, which I don't know where they are. I can find the perfect log. So out of the world, the rest 90%, 99% of the world looks completely random. Actually, is random. Only 1% of the data allows me to sparsify. There's a very simple procedure. very efficient procedure to find it. This is magic. Whatever we said about scaling law, nothing compared to this. 哇，小学生的东西跟这个东西其实比这个你脑袋想做就想不出来。为什么 ？Why? How could that be possible？ 对不对？看似是就是这种用这种算法去 discover structured powers unimaginable， 对不对？完全是 embedded in complete apparently complete noise. Yet we can discover it with a very small of data. And this is emergence. Right? This is how high-dimensional statistics, high-dimensional geometry, physics, right? This is how when this kind of phenomenon is associated with why quantum becomes deterministic. Okay, from random world, uncertainty become certain. What we observe here is completely certain. Where is that surface? You're saving all the space transition. 这才是 emergence. 这才是 quantitative leap. 明白吗？包括 intelligence, we saw this quantitative leap, right? We don't know why. This may be one of the reasons. 对吧？从 DNA 到大脑，从大脑到人，文字到数学到 abstraction, we don't know. Right? Those are likely the models. Not what we see, more data, bigger model. Wow, we see this curve fit. Well, no, we march into DNA. No, we're not, right? So this is something truly incomprehensible. I mean, there's open problem with why this is, we don't know how far is. Now you actually can experiment with real data if you want. Now you can crop, right? You can take the clean data, of course you learn, right? Then you can add noise to it, you learn, right? You can add half of the, say those are completely random image. You still learn. I will still find the basis. Recognize there are some digits in this vast amount of randomness. Also, you can crop 50% of the pixels. You still can learn to clean what's going on, right? And also you can run for patches, tokenized patches, right? Can learn dictionary. We'll talk about that, right? So all the transformer are precisely learning those dictionaries layer by layer. Okay, we'll talk about completely open all the white box, the black box, right? So digits, tokenized patches, even with noise and so on. Right? Ducks, color images, and so on. You actually learn beautiful patterns about how to compress all the images, right? Those spaces will be much more efficient than wavelengths, than Fourier transform for images. 所以为什么现在Google, right? They actually can train neural networks, train a COBOL to compress videos, images much more efficiently than wavelengths, than JPEG 2000, than MPEG, right? This is the reason. You learn, you let the data speak. What is the best transformation? Find the most sparsifying transformation, most compressible structure. Right. So those are the things. You can run a bigger data set, right? This is a bigger experiment. We train about 100,000 random A by color patches from CIFAR 10, and you can learn a basis, right? So this is learn from clean CIFAR, learn from CIFAR with Gaussian noise, and learn data from CIFAR with 20% Gaussian outliers, and learn basis from with 50% sparse corruptions. You can see all the top bases learned are almost exactly the same. 对不对？很有趣 ，right? So it always tends to identify there's a common base. Doesn't matter you cropped it, adding the outliers to it, crop them, adding noise and so on. They always learn converging to the same patterns that at least a fraction of the data, the structure of the data. That's precisely what our brain is doing. Despite we see all this noise, incomplete data, corrupted, occluded, we learn something quite stable, right? Despite all the variations, right? So if you want to know, right, see the message. I want to summarize the message. Remember, we have very pessimistic message, 对吧？非常悲观，对吧？就早期这个学 dictionary learning 开始会很悲观 ，right? Oh, this is bilinear NP hard problem. Also, even you can solve the bilinear problem, the sample, even the computational cost is not a burden. The sample data complexity is a burden, right? Is n choose k. You need combinatorial sample, be able to identify the structure, which is completely untrue. You only need the correct n squared combinatorials. And also, right, the algorithm, it's not greedy descent. Right? Yes, greedy descent works, but it's very, very slow. Okay? Yes, backpropagation works. It's very, very slow. Turns out the most powerful family of algorithms, starting from Newton, is trying to solve fixed point map, contractive map, power iteration. You only take dozens of iterations, you're done. Not thousands, not thousands of epoch, right? 现在动辄训练神经网络，对不对？让上对吧？几十万个 epoch, right? GPT-4, GPT-3, right? I think it's like 30,000 epoch, right? To converge. That's completely nuts, 对吧？从优化角度，那简直是笨得一塌糊涂啊！那自然界早就淘汰了，这样的生物早就死绝了，对不对？就花那么长时间去学，对吧？Our brain, you know the cortical cortex, right? Our brain is the maximum depth, depending on how you count it, is about 6 to about 12, about a dozen layers. Okay? That's how efficient we process our signals, transform our data, reach a very high level understanding of the data. 你需要1000次迭代，早就死掉了。OK? Cannot afford that. OK? Also, we cannot afford backpropagation even. Okay? We're doing a lot of much more clever things. So now you can see there's a lot of magical things. So we don't understand how we have a data in the high dimensional spaces, the statistics, the geometry, right? And yet, the classical analytic approach has told us so much about things we don't know yet. We don't comprehend them. Even linear model, even Newton algorithm. Do you really understand it? Do you know the history? Do you know why they solved the problem? What problem they intend to solve? Not necessarily what you learned in the past. Okay, try to get that history. Newton says we stand on the shoulder of giants. Make sure you know where the shoulder is. Okay, whose shoulder you're standing on. Then understand that very, very well. Then you have a firm foundation, right? To truly be able to add a little bit delta to the human knowledge. Only you understand what we have done, understand the shoulder precisely, so you know where we're standing, right? So we understand what we have contributed, have not contributed. Right? So this is the conclusion for the analytic approach. I actually really like this body of knowledge, and so correct a lot of, right? Since 我们这些想当然的一些做法。甚至很多刚才早期的这种 early those perspectives, right? Those by the top mathematician in the world. Okay, think this class of problem is impossible. Right? I'm pretty sure each one of them has the ability to solve the problem. But what's stopping them is early misunderstanding. They think it's too hard. 知道吧? So the last couple of minutes, I tell you a story. Right? So Zhang Ye got a PhD in 2 years, right? So there was another student at Berkeley got PhD in 2.5 years, right? So he actually one day, one of the professor assigned final projects, and he will always hide like 3 open problems in a list of 10 problems students select, right? So one of the students actually come to very unfortunate. He chose one of the open problems for his final project. He almost had a mental breakdown because he couldn't solve it until he almost gave up. But one day he went to a soccer game and realized there's an idea that he solved the problem, which is an open problem. He got a PhD, right away after he solved the problem. So hence there is a point about mentality. What is creation? What is invention? 对吧? The mentality 很有趣. What's the difference between homework and a research problem? Actually, the difference is your psyche. 你的心理。为什么 ？homework 老师给你 homework， 你为什么会鼓足勇气去解呢？老师是肯定有答案的，这个问题肯定有解的，对不对？老师肯定是知道的。research 不一样 ，if you dedicate it， 所以这就是做 research 很重要的事，就是你的对吧？信心很重要，或者 faith 很重要。你这个 problem， 你看。你去不去做，是你早期你相不相信这件事情有好？Do you
believe it has a solution, right？ 所以很多问题，如果我把一个 homework 交给你，我说这是个 research 问题，你们肯定很多人不愿意去做。为什么？马老师都不知道答案，我怎么有这个本事去做呢？对吧？但 maybe you have， right？ Basically 的心理作用会非常影响，对吧？知道一件事情能做，不知道一件事情能做，这个 prior 是很重要。明白我意思吗？So you try to do that. When you do homework, when you do research, and it turns out in the future you'll find that probably there's not much difference. It's all about your confidence, right? 所以像这些非常有名的，我就不说谁了，对吧？非常有名的数学家，最早说这些问题 dictionary 是不能解的问题的时候，他们可能有他们的理由 ，right? Then those turns out all those reasons are very superficial, right? I mean, at times sounds very reasonable, by the way, right? Even people in the field find it's completely reasonable, very even convincing, but yet not rigorous. There's a big difference between something convincing versus something rigorous. So there's a lot of things said that people said about AI these days. Sounds very convincing, but they're completely not based on scientific, mathematical evidences, reasons. Okay, there's a very big difference. Hence, for all this course, hopefully we'll try to do this through understanding the classical story, even in the analytical approach, which is supposed to be very rigorous. Suppose people think they know everything, right? They can make a lot of stupid mistakes. Let alone the current AI practices a lot of heuristic, a lot of trial and error, a lot of misunderstanding, right? I'm pretty sure there's a lot of statements made about AI or current systems. It's completely untrue. And we're in the process to discover those things, right? So that will take very, very different methodology and even very different mindset. Many people think we don't have to understand. Many people say we don't need to understand, right? Or many people say maybe there's impossible to understand, right? No, maybe we should, right? The same thing. Now, why we have the courage? Because we see cases like this. 我们看到，对不对？ dictionary 这样的问题。就是这样的问题，哪怕最 top 的数学家也会犯错，包括对一范数的理解 ，Boscovich 的理解也是这样的，大家都会有很多的这个误解。So this is actually the era we live, right? There's a lot of mystery things. There are things that are truly magical and deserves us to our attention. But many things that many people think are magical just because they're ignorance. Right? They don't know optimization. They don't know high-dimensional statistics. They don't know the computation, right? The phenomena in high-dimensional statistics, high-dimensional geometry, in optimization, that people have understood much, much deeper, and can explain, or cannot explain even much more magical, mysterious phenomena, right? Not of the kind we saw empirically in many of the data and so on.